In this video, we're going to be looking at multiple different collisions and approaching them using the idea of the conservation of momentum. And the main goal is to take a look at a couple different examples and be able to implement these ideas and strategies with any type of collision problem. So first of all, we got a couple pictures up on the screen, but more than likely you're actually reading a word problem, not working out a problem based on pictures. So make sure you draw the pictures for yourself. So I would set them up horizontally and set up things before and after the collision. So because we know that the momentum is conserved, then we know that all of the momentum of each of the things in the system sum up to the same amount of everything after. So I write them horizontally so that I could put a big equal sign in the middle and then do all my calculations to the left and right of the equal sign. Now we have a scenario where we have a 2 kilogram cart going at 2 meters per second, a 1 kilogram cart moving towards it at 3. So one of the key things is to recognize that this is negative. So generally speaking, I would just say everything to the left of the screen is negative and everything to the right is positive. Now afterwards, we still have the same object. So this is still 2 kilograms and 1 kilogram. And my question is, if this one gets bumped backwards at 1.33 meters per second, then what's the final velocity of the 1 kilogram cart? Now again, because the 2 kilogram gets bumped backwards, we're going to place the negative there. So that's why the pictures are going to be pretty important in recognizing which things go in which direction. Now, what we're going to do is we're just going to set up the mass times velocity for each of the objects before and after the collision and see what we get for the final velocity for a 1 kilogram cart. All right, so we came up with positive 3.66 meters per second. So I just took the product of the mass and velocity for each one of the things. And like I said, I like to set up my pictures horizontally. So then it makes my numbers nice and organized so I can just literally slide the numbers from my picture straight down into my formula. And then that really helps with the organization. So as I said, I just found the product of the mass times velocity for each one of them. I did 4 plus -3 to get positive 1. Total momentum is 1 for the entire system. This one is negative 2.66, so I added 2.66 to both sides. And then this is just 1 VF, so the 1 basically drops out. It's not really that significant mathematically. And then we get a final velocity of 3.66. So because the answer came out to a positive number, that means that the cart got bumped over to the right. So it got bumped backwards. Now let's take a look at our second scenario. We are doing a same sort of thing, but this is considered a perfectly inelastic collision where two things connect to each other, which is a pretty common scenario to look at in physics. And the setup is going to look very similar with some slight differences. So let's go ahead and work this out and see what we get for the final velocity when these two carts are stuck to one another. So the key to solving this problem is actually treating these two masses like a single mass. So although they are 2 and 1 kilogram separately, it's kind of like one big 3 kilogram object. So we only need one m times v for the after the collision portion of our setup. And the total momentum was still 1 because it was the same initial conditions, except they just happen to stick to each other. Um, and then we just divided both sides by that mass of 3 to get the final velocity of 0.33. So both of those carts would have a velocity of 0.33 meters per second. And again, because it's positive, that means that everything's moving to the right. So with these problems, a lot of it is really just making sure your numbers are organized. If you draw a picture with arrows, include your negatives, and then drop your numbers straight down. The rest of it is not too complicated from there. You just have to work out a little bit of algebra and then solve from there. All right, so let's go ahead and erase this screen. I'm going to bring up a couple different ideas. One, talking about explosion collisions, and then two, analyzing the amount of kinetic energy of the system before and after to figure out some different values. All right, so the third scenario we're going to take a look at, as far as collisions go, is an explosion collision. So we did a perfectly elastic collision, which was the first one that we did over here. We did the inelastic where they connected, and the explosion one is just the opposite of the inelastic, where the two things start together and then they separate afterwards. So the key to these is similar to the inelastic, to where both of the masses are combined. So in this one, the thing that sort of confuses people sometimes is there's actually no momentum in the beginning. Now, there can be explosion questions where two things are together and they're moving, and then in that case, you just plug in a velocity. But this one in particular, both people are sitting in these carts at rest. They push off of each other, and now they separate. And then I just added the two people in here, so I'll go ahead and put them in here as well. And after that, you would go ahead and solve the problem as you normally would and do the mass times velocity for both of the different objects. Okay, I included the negative in there because it's going to the left. So it becomes 0 equals -6 plus VF. Add 6 to both sides. It's going to be 6 meters per second for our final velocity of our 1 kilogram cart. So like I said, very similar to the perfectly inelastic collision, just kind of flipped around the opposite end where the masses are combined and then they separate from one another. Now, the last thing we're going to take a look at is doing an energy analysis. So to find out if it's perfectly elastic, then the amount of kinetic energy is conserved. What that means is that the sum of the kinetic energy of all the things before the collision equals the sum of all the kinetic energies after. So all you really have to do is, once you have completed your conservation of momentum problem and have all of your M's and V's, you're pretty much good to go. So we already got this velocity a little bit earlier. So all you have to do is do 1/2 mv squared for both the objects before and after, and see how those two numbers compare. Now, if I took the kinetic energy of each one of them, it's just 1/2 mv squared. I sort of ran out of room here, but these are the two things for after the collision. And I got energies of 4 and 4.5 joules to sum up to 8.5 joules. And then afterwards, it summed up to 8.48. So it looks like maybe because of a little bit of rounding and approximating, my energy was off by a tiny bit, but I would basically consider those to be the same. So therefore, it would be an perfectly elastic collision in that case. And then if these two weren't equal and there was some significant difference there, then you could consider that to be inelastic, but just not perfectly inelastic, or else they would have stuck together. So if you want to do an energy analysis, as I said, you would do the conservation of momentum ideas and calculations first, so you have all the M's and V's. And then from there, if you do the energy analysis, the 1/2 mv squares are pretty simple. All you have to do is plug them into the formula and see how the before energy compares to the after energy. So I hope that was helpful in helping you analyze and solve momentum and energy problems for these different collisions. Thank you for watching and listening.